And the talk will give a brief summary of this book, which we are now finishing to prepare. And this book also summarizes the work made by Professor Santilli during all these years on the hadronic and many others on hadronic mechanics. So this is our conference site. This is Professor Santilli, and I will start from two different views on two different views on physics. First is macroscopic mechanics, and the second one is microscopic mechanics. Macroscopic mechanics is classical mechanics, and it deals with observables. And this mechanics is summarized in the well-known Hamiltonian equations, where the derivative of coordinates and time derivatives of impulses are written in the form of derivatives of the Hamiltonian, and Hamiltonian is the total energy of the system and the sum of kinetic energy and potential energy. But in these equations, in more general form, we have also this term, which we already spoken about today. This term describes non-potential interactions, and this is non-potential force, which cannot be written in the form of derivative, and it cannot be written in the form of potential force. So when we take some observable Q and write equation, its time evolution, we can write it using such well-known structure as Poisson-Lie brackets, or Lie brackets, or Poisson brackets. And in the case of this external force, these brackets have this additional term here. And in this case, these are more general brackets than these ones. And the problem is that in that case, these more general brackets are not antisymmetric. And so we have, and the Hamiltonian equations with this external term, they do not conform to the Lie symmetry. So the counterpart of these equations on quantum levels, when quantum mechanics originates from the Heisenberg unidentity, that we cannot measure simultaneously impulse and coordinate. And when you come to these quantum scales, you have to come to the quantization and operators instead of observables. And so quantum mechanics deals with operators. And we can write the same equation as in the classical physics, but in terms of operators, where the time derivatives of operator of coordinate and operator of impulse are written as derivatives from the Hamiltonian operator, which is now operator energy. And quantum mechanics, as was classically formulated, it has zero non-potential term. So we do not have this non-potential interaction in quantum mechanics. And so quantum mechanics, it was not built to take into account this non-potential and non-local interactions. In the same way, in this case, when we have zero here, quantum mechanics can be reformulated over the Lie group structures and Lie algebras, and we can build these well-known Lie brackets, and time evolution of any operator can be written using these brackets, and also time evolution operator of U. So what was proposed originally by Professor Santilli is the task which had to be done is how to take this non-potential force and first to write it in terms of Lie algebras and Lie structures, Lie-admissible structures, and second how to take and incorporate such terms into quantum level. so this was done during all these years in hadronic mechanics. First, these brackets were generalized to a more general brackets, and this transformation was called mutations of Lie algebras. And mutations of Lie algebras is the more general form of the well-known deformations of Lie algebras. There are P deformations, Q deformations, and mutations are more general form. So we can build more general brackets in this way, where lambda and mu are constants, and to build more general evolution of some operator. And in that case, when we take these constants here, the solution of this equation, it is written in using other evolution, more general evolution operator, and this evolution operator is not a return operator, because this product is not is not identical operator. But these brackets, new brackets, they turned out to be Lie-admissible and Jordan-admissible. Lie-admissible means that when we write this more general, when we write symmetric, we may symmetrize these brackets and anti-symmetrize the brackets. We preserve the same structure of the brackets with constant. This is called Lie-admissible and Jordan-admissible. And so the second step was to generalize these brackets for operators. When instead of constants we put here some operators. In that case, R and S. And so this was also done during these years. And again, we can reformulate equations using this more general form on the operator level. And less general form is when operator R is equal to operator S. In that case, this is operator T, and these equations were called Lie-isotopic equations. To work with these more general brackets, one had to build new numbers. Because all numbers, complex numbers, real numbers, and known numbers on that time, we could not work with these new brackets using these numbers, because these numbers should conform to the structure of these operators and these brackets. And so first we shall speak about isonumbers. Let us select some numerical field of known numbers. Numerical field means that we have some set of numbers, and we have defined operation of multiplication and operation of addition, and corresponding units, iths for multiplication and zeros for addition. This means numerical field. And the idea proposed by Professor Santili was to change this unit. And so we can introduce new unit, I hat, which is positively defined. And this iso unit is not from this original set F. And then we can use this iso unit to build different, iso multiplication using this definition when we put this t into this between these two numbers. And in that case, we can iso multiply this iso unit with old numbers and to derive new numbers, which were called n hat. And in that case, we can build what is called iso numbers and iso fields. And iso fields is f hat, which are composed from these iso numbers. And so For example, if we have if we take iso unit equal to 1/3, then iso product of 2 and 3 will be 18. 2 multiplied by 3 multiplied by 3, and in that case, for example, 4 is the prime number. These iso numbers, then iso numbers allowed to take and to incorporate that non-local, non-potential term written in the Hamiltonian equations into the V formulas. If we choose the units, iso unit and responding to coordinate and iso unit responding to time in this form, and write rewrite the Hamiltonian equations in iso form, then we get the same equations written in classical English. So in this way, by selecting these iso units, we can incorporate non-local and non-potential terms into the equations which preserve the structure with these new brackets and new numbers, iso numbers and iso brackets. And so the idea, if we speak it very robustly, is the same. If we have some complex physical system which is non-local, non-potential, and so on, we can try to select completely other unit for this system from the point of view of mathematics, and to incorporate all the nonlinearity, all the non-potentiality, and all the irreversibility into this unit. And all this will be hidden here in this unit. And based on this unit, we can recover all the equations in the classical form. So this is the key, this is the milestone of all this theory. So then we can speak about general numbers. It is not seen properly here, but general numbers, we have already talked about them today, and so they were introduced to take into account irreversibility, to distinguish between forward product in time and backward product in time. So I will not repeat the previous presentation. And also hypernumbers, about which we had a lot of presentations yesterday, I will also repeat it. Now I will briefly describe some applications of this theory of hadronic mechanics to some problems in physics. First, we shall consider the well-known quantum mechanics equations, Schrödinger equations, and evolution of some operator written over ordinary brackets. If we consider some complex nuclear physics problem, when we have very strong non-potential interaction between some two particles, in general nuclear physics, they modify this. They try to take into account this interaction using this potential in Hamiltonian operator. And because these forces are non-potential, they require to take a lot of different terms in Hamiltonian, to take into account all different corrections and to fit this potential energy to different experimental data. And so this how the ordinary nuclear physics and quantum physics work. what can be done using this new formulation, using isomathematics, using hadronic mechanics? We can, again, it is not seen well, probably I can. Oh, hence horizontally isotropic equations. These are two tubes filled with air, and there is laser in one of these buildings, and their spectrograph in the other. And so the light of laser was passing through these tubes, and two different conditions were selected. First condition was when there is air in the tube at atmosphere pressure, and the second condition was when the air here was under big pressure, about 100 atmospheres. And so the results of these experiments are plotted into this figure. This is the spectrum of laser light when there is atmospheric pressure in the tank. And this is the same spectrum when the medium is more dense than pressure. It is under pressure. And we can, and there is a detectable shift of wavelength by about 0.5 nanometers. And this shift, it can be used as an experimental confirmation of the prediction of isospatial relativity regarding isored shift of light in dense medium. And to finish my presentation, I would like to speak about other applications of hadronic mechanics which are reviewed in this book. For example, we have very big applications in quantum chemistry. And for example, corrections for the energy of H2 molecule, water molecule, and also different studies of magnetic gas technology is a gas which is produced when we have some plasma conditions, when we put some arc, electric arc into medium, and apply a very high voltage to that arc. And there forms high energy plasma around this arc, and this plasma, it produces gas. And this gas was called magnetic gas. And this gas is not ordinary gas because it has some extra energy in it. And this extra energy seems to be due to the existence of some hidden magnetic bonds in these molecules, and these bonds were called by Professor Century magnecular bonds. And these magnecular bonds were seen on different experimental conditions, on chromatographs, on spectrographs, and so on. And so also there is a lot of studies made by Professor Animalo and Professor Santello on ISA superconductivity. Yes. And these are hadronic reactors built for industrial production of magnetic gas, and also for experiments on nuclear physics and for the synthesis of neutrons. And there was a confirmation of Don Carlo Borgi experiment when we have klystron, simple klystron filled with hydrogen. And when we put this arc and apply high voltage into this arc, and neutron detectors, correct and suitable neutron detectors, they show that the generation of such particles which we can call pseudo-neutrons. And this pseudo-neutron then can be used in some industrial applications to produce different clean energies using nuclear energy. And so this is a brief summary of what was done during these 2 years in the field of hadronic mechanics, and I would like to thank Professor Santulli for inviting me here. And so thank you very much for our cooperation, and thank you very much for attention.
Professor Ganz, I have to correct you, it's the other way around. The idea of seeking the Higgs boson has no physical sense. Once you admit that the proton that enormous impact has new non-potential interaction, because you have automatically a renormalization of the mass. The equation that Professor Ganz showed you, where there was the Hutton potential, then you look at deeper, you see the mass also from the isospatial relativity. You see the mass is changed, becomes renormalized. And so the very numbers that I'm looking for is under a long list of theological assumptions. First, that inside is impacted, quantum mechanics is exact. Secondly, that space-time is not altered, etc., 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 under an enormous number of assumptions, or each questionable. In reality, the phenomenon is enormously more complex. What's going on? Unfortunately, at CERN, there is not even a shadow of scientific democracy. So this problem, they gulp hundreds of billions of dollars, and with no discussion is allowed. I don't think I will ever be able to deliver a seminar at CERN to even touch those arguments. This is a situation where, I mean, Italian born or many European, you should know, you pay those people. Basically for this, what I said before, the most form of slavery that of the mind, with no scientific democracy. Also, like to indicate that indicated Magnegas, why we were forced into the lifting special relativity. Why so? We are talking about the fundamental point. We are talking about an arc within liquid. Remember, everything we did was for machines, with fuel and energy. Everything came from concrete machines. Well, there. Imagine so this arc and is in a liquid. Okay, what do you need first? The resistance. Question: can I define the resistance out of Maxwell equations? Of course not. Can I define the resistance with Einstein's special relativity? Of course not. Can I define the resistance in quantum mechanics? Of course not, ladies and gentlemen. So this was enough for me to prohibit me to even think of 20th century theory for new energy. Then it was, however, if you do the lifting, indeed, you are indeed. And finally, I'm sorry, I won't take too much time, but finally, we don't have time to indicate cosmological implications, but incidentally, you can see the normalization of the mass from the first axiom of the special relativity, the quantum mechanics, that the maximal causal speed is altered because of the alteration of space-time. And I don't want to make additional comments. Thank you.
I have a question regarding the, so that's a correction to the Coulomb conjunction.
It cannot be said correction, because at short distances it is the predominant term in this interaction.
Yes, but it came out as the result of this operator, this T operator.
Yes.
Well, let me interject in this way. If you think about potential, you have a chain of inconsistency. You chain. For instance, when you got the relativistic, this was a projection, what the professor correctly did, what he did is a projection of hadronic mechanics in the space of quantum mechanics to let you see the equation. But at non-relativistic level, the moment you get it, we have also the relativistic counterpart, it's sinus of the proton. And then the notion of potential, you can even formulate, this approximation is gone. Or I strongly recommend you don't even dream in this field of quantum mechanics, because you have a chain of inconsistency that will remain unknown to you. Later you will recognize. Think in this way, the proton, the rest energy of the proton is bigger than the sum of the rest energy of the electron. The rest energy of the neutron is bigger than the sum of the rest energy of the proton and of the electron. Therefore, you need a positive binding energy with quantum mechanics. This is anathema. The Schrödinger equation is totally inconsistent. All consistent bound state in quantum mechanics needs a negative, you have a mass defect. Here you need a mass excess. So what you have seen is just an approximation on a relativistic project in our space-time. But the moment you see that the quantum mechanics is unapplicable because of this fundamental rule, breakdown in the Schrodinger equation, then theory of potential is very insidious, very, very insidious.
Any other questions?
Yeah.
Thank you.
Beautiful, actually.
Thank you.